this lecture. In today's lectures, we will talk about the strong nuclear force. I'm Dr. Pervaiz Ahmad. So, what is a strong nuclear force? Uh, a strong nuclear force is a force which can hold a nucleus together against the enormous force of repulsion of the protons. This is indeed a force which inside the nucleus hold the nucleons together in spite of their mutual repulsion due to the Coulomb repulsive force. Just like you can see it here in this particular figures. It's the inside structures of a particular nucleus it's almost all the students working are studying the nuclear physics. They know that the nucleus contains neutrons and the protons. The neutrons they are the charged particle, while the protons are positively charged particles. So, it's a very obvious fact that the protons being with the similar charge, they can repel each other. So the questions, which the people have in mind that how, in spite of the mutual repulsions between the protons, how the nucleus remains stable. So it's the discovery of the nuclear force, the concept of nuclear force that explains the fact that when the particles they are close enough, just like in the nuclear range, so they're being acting by the strong nuclear force, just like you can see it here. And the strong nuclear force, the force that act between the two nearby nucleons. This the force, unlike the Coulomb repulsive force, which is attractive between even neutron and protons, or proton and protons, and neutron and neutron. And it's a short range force. Irrespective of whether it's a neutron or it's a proton, so it's operative on, uh, it's operative on both are being equally. So it does not obey the inverse square law, just like we have for the electromagnetic force. You know that the electromagnetic force is basically is governed by the Coulomb's law, according to which that the force of attraction, the repulsion, is proportions to the product of the magnitude of the magnitude of the charges, and inversely proportion to the square of the distance between their centers. So unlike that, the strong force which acting between the nucleons inside the nucleus and which hold the nucleons together inside the nucleus is independent of the inverse square law, just like we have that for the electromagnetic force. Uh, but we remember there are some facts about the strong nuclear force which everybody should know about. Uh, this fact you can also this fact you should also know that the strong nuclear force it's a short range force. What it means it's the short range force. By short range we mean that it's only stronger when the nucleons inside the nucleus, irrespective of whether it's the proton or it's the neutrons. So this force will be the strongest ones if the nucleons they are lying at a distance range of 10 raised to a power minus 15 meters. So this is why we are saying that the strong nuclear force, a very short range, is acting at a very short distance. When the nucleus has this much of the separations, so the strong nuclear force will be stronger as compared to any other force. From any other force here, we mean the Coulomb repulsive force, which is being operative between the two protons. So exchange particles are ions and other heavier particles. The particle which is being exchanged during the strong nuclear force. These are being the ions and the other stronger particles, the heavier particles, which we may discuss later on in some of the coming lectures. The range of the particle exchange force is limited by the uncertainty principle. So you know about the uncertainty principle. So is this uncertainty principle is basically do what the range of the particle exchange force is limited by the uncertainty principle. Uh, the next point is it's the strongest of all the fundamental forces. And this fact we have explained in some of the previous lectures when we were comparing the relative strength of all the forces. It's the obvious fact that this kind of fact is the strongest of all the fundamental forces. So, however, there are some facts where everybody should know that, okay, and it's that it's extremely small separations between the nucleons. The force is repulsive, which keep the nucleons at a certain average separations. I mean, you should know that as long as the particle has the separation, just like we mentioned in the first point, that is the separation. If the separation is in the range of 10 to the power minus 15 meters or smaller, so we will have the strong nuclear force at the strongest one. But as the separation increases, so then you know that the Coulomb repulsive force between the protons, it will overcome the strong nuclear force, and it's the points where we saying that the nucleons go towards the instability. So it's the fact that all the people or all the students should keep in their minds. So some of the properties. Now we move towards some of the basic property of the strong nuclear force. So what are these properties? So the first property of the strong nuclear force is that the nuclear force or the strong nuclear force is a short range force. So what it mean? It mean that at a short distance, uh, just like we mentioned on the previous slide, it is stronger than the Coulomb's repulsive force between the protons. So nuclear force can overcome the Coulomb repulsions of the proton in the nucleus. So due to its strength, it's easily overcome the Coulomb repulsive force. But to what extent? The extent we mentioned, that is when the nucleons are at the range of 10 raised to power minus 15 meters or smaller. But as the separation increases, so then the Coulomb repulsive force is overcome the strong nuclear force. It's the first characteristic of the strong nuclear force. So at long distance, that is in the order of atomic size, the nuclear force is negligible. I mean, it's the obvious fact we're talking here about again and again. That is, when we increase the distance, we increase the separation between the nucleons, which what it mean at large distance or at long distance. How much long this one? That is in the order of the atomic size. The atomic size, you know that we refer to normally 10 raised to power minus 10 meters. So the nuclear force is negligible. I mean, if we talk about a nuclear force at the range of the atomic scale, so at the atomic scales, the nuclear force is negligible. And also be remember, just like you can see it here, the strong force is only operational between the nearest neighbor. That is, you can see it here. That is, I mean, it's only operational among the nearest neighbor, and the nucleons which are far apart from one another. So in that particular case, I mean, their nuclear forces are negligible. So it's not like the electromagnetic force. I mean, which we can say that it can act at any distance. I mean, which can act at a long range. So the property number third, that nuclear force, not all the particles experience the nuclear force. What it means? You know that inside the nucleus, we not only have the proton and neutrons, but in other words, we can say that we have a sea of particles inside the nucleus. So it's also a obvious fact that inside the nucleus there are some particles which are free from the action of the strong nuclear force. I mean, some of the particles which we will discuss later on in some of the lectures. I mean, so we will say that we will discuss that there are some particles inside the nucleus, or a group of the particles inside the nucleus, which do not experience the strong nuclear force. So be remembered. What actually we mean by this point, that not all the particles experience a nuclear force. So it means that inside the nucleus we have neutrons, protons, and pions, and their building blocks, that is quarks. I mean, all these particles, that is neutrons, protons, and pions, they are being built from the quarks. Uh, and how they are being built? They are being built from the combinations of the quarks to the strong nuclear force. What it means? It means that the quarks, which are, I mean, the basic building blocks or the fundamental blocks, uh, or the fundamental particles, they are being bound by the strong nuclear force in the form of neutrons, protons, and pions. So, unlike the quarks, there are also other group of the particles which we call leptons. So leptons, they're basically a group of the particles which includes electrons, muons, and neutrinos. So these are the particles which are basically immune to the nuclear force. What it means? It means that the strong nuclear force is not reactive among these particles. So that's why we're saying that these particles, they are not immune to the strong nuclear force. So this is the actual meaning of the point number 3. That is, not all the particles experience nuclear force. Point number 4, nuclear force includes a repulsive term which keep the nucleons at an average distance. So the nuclear force shows uh, saturation property. I mean, which already we discussed that. I mean, the nuclear force is only operational among the nearest neighbors. So the nucleons which are far apart from each other. So I mean, the nuclear force is not operational among the particles among the nucleons which are far apart from each other. That's why we're saying that the nuclear force shows saturation property. Point number 5, or properties number 5, each nucleon just interact with its nearest neighbor, and so sees the same environment independent of how many nucleons there are at a larger distance. I mean, just like we can see here, if we have a proton, we consider only the proton, so the force among the proton is repulsive. But here we say that inside the nucleus, if the nucleons are at the nuclear force range, here what actually means by this particular point, it's saying that each nucleon just interacts with its nearest neighbor. So here you can see that if the nearest neighbor is the neutron, so there will be the strong nuclear force between the neutron. That is, neutron will attract the proton and proton will attract the neutrons. So unlike that, if the nucleon is far away, just like you can see it here, this proton is far away from this proton, so there will be no force, no nuclear force between this proton and among between this and this protons. So the nuclear force is only operations between the nearest neighbor among that is the particles which are very close to each other. Nuclear force depends on the spin. I mean, just like we mentioned previously about the electromagnetic force that we mentioned that the electromagnetic force depend on the charge. So similarly, the nuclear force depend on the spin. So that's why you're saying that. I mean, it's all you know that the neutron is the chargeless particles. So that's why we say that there is no electric force between the neutrons or between the neutrons and the protons. But everybody know that the neutrons, they are being the fermions, and the fermions, they have the spin, and their spin is equal to 1 by plus minus 1 by 2. So just because of that spin, the nuclear force is being experienced by the neutrons and protons equally. So I mean, it's the property. It's one of the basic property of the strong nuclear force that it depends on the spin of the particles. Uh, Properties number 7. Nuclear force is charge independent. We already mentioned on the previous point that unlike the Coulomb repulsive force between the protons, nuclear force do not depend upon the charge of the particle. So that's why we're saying that a Coulomb force or nuclear force is charge independent. So force between the neutron is same as the proton and neutron photons. I mean, charge dependent. The basic difference between the protons and a neutron is a charge, that is proton has a charge equal to 1 while neutron is electrically neutral particles. But if we consider strong nuclear force, so strong nuclear force is equally effective for the neutrons and neutron. That is, uh, strong nuclear force between the neutrons and a proton is the same. I mean, the strength of the force is the same. It's only depend upon the distance or the separations between the nucleons. Uh, Point number 8, or the property number 8, that is the nucleon force has a non-central or tensor component. What it means? It means that this part of the force does not conserve angular momentum, which is constants of motions under the central force. I mean, this point we will discuss later on in some of the coming lectures. So these all we have for the strong nuclear force and some of the basic property of the strong nuclear force. In coming lectures, we will come with some more details about discussions about the nuclear physics. So till then, bye bye.